Okay, this is meant as a review of a couple of concepts that have been covered previously. So that's polarity and looking at some of the VSEPR geometries and Lewis structures. So as a reminder, when you have covalent bonding or just bonding type in general, one important concept is polarity. And so polarity is how different is the charge spread out around the molecule, around the bond. So the disparity in how that charge is distributed. So when there's a much higher difference in electronegativity, an extremely high difference, then you can have what's called an ionic bond, where electrons are actually transferred from one atom to the other, creating charged ions, and therefore the attraction is just the attraction between those oppositely charged ions. What we're focused on here is when the difference in electronegativity is a little bit less, somewhere in the medium to low to very low, and actually zero difference. And that's going to put us in the covalent type of bonding, where electron pairs are being shared. Up to around a difference of about 1.8 is a rough guideline for the difference in electronegativity. Bonds will remain covalent, so the electrons will still be shared, but the higher that difference gets, the more the electrons are not being shared evenly. And what happens as a result is that when electron pairs are shared unevenly, you end up with partial charges on either end of the bond. So the side where the electrons are pulled more closely to, and the electrons spend a little bit more of their time in that part of the bond, gets a partially negative charge, and where the electrons are being pulled away from gets a partially positive charge. However, if electrons are shared evenly across a bond, because the electronegativity difference is extremely low, about 0.4 or less, then the bond can be considered completely nonpolar covalent, meaning that electrons are shared evenly, and so there's no partial charges that result. Okay, so some pictures that represent this: you've got the electron transfer of ionic bonding, you've got the uneven sharing of polar covalent bonding with more electrons next to the chlorine atom in this HCl molecule. And then you have completely even nonpolar covalent sharing in a diatomic chlorine molecule. Okay. Just some very simple molecules to start of polarity examples. Any of our diatomic molecules, so any of the Brinkelhoff elements that exist as simple diatomic elements, so Br2, for example. When bromine bonds to bromine, clearly bromine is going to have the same electronegativity as itself. And so a bromine molecule, if the only two things in the molecule are bromine, well, it's going to be a perfectly nonpolar molecule. The charge is going to be distributed evenly around the entire molecule, and so it has absolutely no partial charges, no permanent partial charges in the molecule. So diatomics are probably the simplest ones to identify. They are all completely nonpolar, because when something bonds to itself, there's no uneven distribution of charge. Another example, this came up on a recent exam question, is that phosphorus bonded to hydrogen. Based on where they are in the periodic table, you might predict that they have a difference in electronegativity. Most people would predict phosphorus has a higher value of electronegativity. But if you actually use the data booklet, there's no difference in electronegativity. And if there's no difference in electronegativity, then all the bonds are nonpolar covalent. And if all the bonds are not nonpolar covalent, then this molecule overall is going to be have even distribution of charge, and therefore be totally nonpolar. There are also some examples, very simple binary 2-atom molecules that are very obviously polar. In this case, hydrogen has a electronegativity of 2.2 and chlorine a value of 3.2, making the difference between them 1. That's definitely in the polar covalent range, and therefore we know that the element that pulls more on them, that has the greater electronegativity, will pull the electrons more towards itself. So if we use one of these arrows, the dipole arrow would be drawn like this. Dipole arrows get drawn with a plus sign as their tail next to the element that has the partially positive charge, and they show where the electrons are being pulled, and so this chlorine would have a partially negative charge. So there's different ways to represent polarity. This is called a dipole arrow, and you can also use those small little delta symbols that were used on the previous page. Those are also acceptable, something like that. So small delta negative, small delta positive. You can sometimes also use what's called a net dipole arrow. So it doesn't work for these two examples, but as we do more complicated ones, if you're adding up the net effect of all the different dipole arrows, you can then do one overall resultant dipole arrow to show the polarity. Carbon and oxygen would be very similar to the previous one. Carbon has an electronegativity value of 2.6 and oxygen 3.4 for a difference of 0.8. Again, polar covalent. And so we would add a similar dipole arrow pointing towards the oxygen. So when there's just one bond, it's really simple. If the bond is polar, then the molecule is also polar. But when things get more complicated, and we have molecules that are made up of more than two atoms, now we need to consider the VSEPR, the separate geometry of the molecules to help us determine if they are polar. Because it's important to have polar bonds, that's a requirement in general to be a polar molecule. You also need to have those bonds pointed and oriented in such a way that they do not cancel each other out. So these are the shapes that you're responsible for knowing in SL chemistry. We've got the two-domain shape, electron domain shape that is linear, two different three-domain shapes, trigonal planar and bent, and three different four-electron domain shapes, tetrahedral, trigonal pyramidal, and bent. And what we're trying to point out here is that the shapes that are most likely to be symmetric, now they don't have to be symmetric, this is just, these are the shapes that are commonly symmetric when they're done this way, are the ones that have no lone pairs. So when something is linear, it has very good potential to have any polar bonds cancel out, usually pointed outwards rather than pointing inwards. I'm not drawing the tails for the time being, just for the sake of time, but if these were dipole arrows, they should have little positive sign tails. So this is a rather common structure. So if the two outer atoms are the same in a linear molecule, then it's always going to be nonpolar, because whatever the dipole on the bonds, it's always going to cancel. The trigonal planar ones can also have three bonds, but those three bonds are symmetrically arranged, and so it's quite possible that they could cancel each other out if they're oriented like that. And the same thing goes for tetrahedral. Although it might not look it on the page, tetrahedral is highly symmetric, and so if all of the outer atoms are the same, then all these arrows will actually cancel down, and there will be no net dipole. Now, for any of these, there's of course a possibility that the outer atoms are not the same. So it doesn't mean these shapes can never lead to polarity, but they're just less likely to. So like in the linear one, if both of the bonds are polar and they both point in one direction, well, then you could end up with a slightly negative charge here and a slightly positive charge here. If you look at the trigonal planar example, to go on top of it, if you had one where the arrow points up and these arrows point towards the central atom, well, then all of these arrows contribute to an overall dipole going up towards this atom. So what I'm getting at now with the green arrows are, when you have these shapes, the outside atoms are not always identical. You might have a hydrogen on one side and a nitrogen on the other. You might have an oxygen up here, but hydrogen's at the bottom. So when the atoms on the outside are different, you have to consider the polarity of each bond and which direction are those bonds pointing in. And then finally, just for this one, you could have an arrow up, and then you could have three bonds that are mostly nonpolar, so they're not really contributing, and so mainly you get this overall dipole pointed up. The shapes with the lone pairs of electrons, with the non-bonding pairs of electrons, are much more likely to be polar, because those shapes, by their very nature, are sort of asymmetric. They, by not having the atom here where the lone pair is, these two arrows are very likely. Let me get back my green. So it's quite likely that this one. Why is it on that? I don't want that. Come on. Let's undo that funky arrow. Okay. So, if this one is pulling that way and this one is pulling that way, well, although they sort of cancel each other left to right, nothing is canceling the pull going down. And so there is a net in this diagram I've drawn. It's quite possible for there to be a net dipole headed towards that side of the molecule. And the same thing goes here. If we have bonds that are all polar and they're pointed in a particular direction, in this case, because of this lone pair, there's no sort of canceling effect going up. And so you end up with a net dipole that would be pointed down. And although this one gets cut off, it would be very similar to the bent one up above. If you have these two arrows pointed down, well, because they're pointed down and nothing is pointed back up, you end up with a net dipole sort of going like this. So shapes with lone pairs are much more likely to be asymmetric and therefore lead to an overall net dipole on molecules. So if you're trying to determine if a particle, a molecule, or an ion, a polyatomic ion, is polar, the steps to go through are, well, draw the Lewis structure, and are the bonds in it polar or nonpolar? Are they essentially nonpolar? So if you had paper 2 and you were looking in the data booklet, you could actually look up electronegativity values, and if they're less than 0.4 different, then you could more or less make the argument that overall the molecule is going to be nonpolar. So if you have, to try to make this sort of like a flow chart of how you would deal with it. If you've got a 0.4 electronegativity difference or less, then if all the bonds are that way, then you would be led to believe that the molecule must be all nonpolar. Okay, because if none of the bonds share electrons unevenly, then overall the molecule should not really have a net dipole. So that's like one guiding way to assess polarity. If one or more bonds have an electronegativity difference greater than 0.4, okay, now you have polar bonds. Still not sure if the molecule or ion is polar yet. So the first step is figuring out, do you have polar bonds, do you have nonpolar bonds? The second step is you should make sure you draw a Lewis structure. Remember, we got our 7 steps. You can go back and review those 7 steps. So draw the Lewis structure, figure out what the geometry is, and if you can, redraw your structure with as accurate a representation of the geometry as possible. Redraw an accurate geometric structure, because it's very easy to draw things on the flat page more symmetric than they actually are. And so if you try to do a more accurate representation of the 3D geometry, it's usually pretty easy to see whether or not it's symmetric. And so the last thing to do is, once you've got that geometry, now you're trying to assess if it's symmetric. So using just these little lines to represent bonds, what I mean by that is when you draw something like water that has an O and 2 H's, it's very easy to draw the O in the middle and the 2 H's on either side like this, and the 2 lone pairs up top, right? So here's what I'm getting at. It's very easy to draw water in such a way that it looks like it should be nonpolar. We know these 2 bonds are going to be polar. The dipole arrows are going to point towards the oxygen, but drawn like this, I think that it's a nonpolar molecule. So what you have to do is, okay, while this is a fine Lewis structure, it would get you full credit. When you count up the domains, the electron domains, there's 1, 2, 3, 4. So you should know this is going to be tetrahedral in its arrangement, which means that it doesn't really look like what you drew on the left. What it looks like is the H's are actually coming off of the oxygen in a bent shape, and the lone pairs are arranged on the other side of the oxygen, and everything's around 105, 109.5 away from each other. And so now, when you draw these dipole arrows, it's a lot clearer that, in fact, they don't really cancel each other out because they're both directed towards the O. And so in this molecule, there's a partially negative charge on the end of the molecule by the oxygen, and there's partial positive charge on the end of the molecule with the hydrogen. So this is what I mean by redraw it. Don't trick yourself with a flat, everything at 90 degrees from each other drawing, because in reality, it works in 3 dimensions and they don't look like that. So number 3 is really combined with number 2 in terms of the steps. You've got to assess your drawing and add in these little net dipole arrows and decide whether or not they oppose each other and cancel out, or whether or not they don't. Okay. So do they oppose each other? Do they cancel each other out? Or are the polar bonds arranged asymmetrically? Is there a net dipole? And so in the case of the water, we would say, if they asked us, is water polar or not? So we would say, yes, water is polar. Why? The O to H bonds are polar covalent bonds, and you could talk about electronegativity difference if you wanted to. And the bonds are arranged in an asymmetric bent shape, so the dipoles do not cancel. This leads to a permanent net dipole, or / an uneven distribution of charge. Okay? So in terms of mark scheme wording, things they're going to be looking for are stating that the bonds are polar and which bonds are polar. So O to H is a very specific way of talking about which bonds I'm talking about. Talking about the geometry, the bonds are arranged in an asymmetric bent shape. So the dipoles do not cancel out, pointing out that the dipoles don't cancel, and talking about asymmetry. And this leads to a permanent net dipole, which is really an uneven distribution of charge around the molecule. If we had an example like CO2, CO2 is a linear molecule where both dipole arrows point directly outwards from the carbon. It would look a lot like this water drawing, except the arrows would point outwards. So in CO2, we would comment that the C to O bonds are polar, again, due to electronegativity difference. But the molecule is nonpolar since the dipoles oppose each other and cancel each other out. There is no net dipole. So that's sort of mark scheme wording for a nonpolar. So in summary, you can have molecules that are or you can have bonds that are nonpolar, and really whether or not they're arranged symmetrically or asymmetrically, it's going to lead to an overall nonpolar molecule because the charge is spread out evenly across the bonds. You can have polar bonds in a molecule and end up being a nonpolar molecule because they're arranged symmetrically, or you can have polar bonds and end up being polar because the bonds are arranged asymmetrically, and so you have overall an uneven distribution of charge. So that's the summary. There are lots of practice examples here, which we'll do some in class. You could try some at home. Draw the Lewis structures, add in the dipole arrows, and try to decide, are these molecules and ions polar or are they not polar?